In this video, we're continuing our discussion of ordinary differential equations, and we are discussing different solution methods for initial value problems. Here we're going to discuss the accuracy and stability of the Runge-Kutta methods. So in the previous videos, the second order and fourth order Runge-Kutta methods have been introduced. So here we're going to take a look at the accuracy and stability of these methods. So first let's consider the general form of the two-stage second order Runge-Kutta method, which we can call RK, or sometimes RK2. And we're using this to solve an ODE of the form x prime is equal to f of x and t. So the solution at a time step ti plus 1 is obtained from the expression shown here. Xi plus 1 is equal to xi plus gamma 1 k1 plus gamma 2 k2, where these functions k1 and k2 are defined sequentially. So k1 is equal to h, f at xi ti, and k2 is equal to h times f at xi plus beta k1 and ti plus alpha h, where this alpha, beta, gamma 1, and gamma 2 are constants that can be determined to ensure the highest order of accuracy of the method. So to establish the order of accuracy, we need to consider the Taylor series expansion of xi plus 1. So that is shown here. So xi plus 1 is equal to xi plus h, x prime evaluated at I, plus h squared over 2, x double prime I, etc. But we know that x prime I is equal to f of xi ti. And if we consider this second derivative term and use the chain rule, we can obtain the result here. So x double prime I is equal to dxi prime by dt. And we know that xi prime is equal to f, so this is equal to df by dt. And we can use the chain rule to differentiate this term, and we see that we get partial f by partial t plus partial f by partial x by partial t. And we know that partial x by partial t, or dx by dt, is just equal to f. So what we get is that this second derivative term at I can be written as partial f by partial t plus f partial f by partial x, evaluated at I. So we can plug these into our expression for the Taylor expansion, and we get the result shown here. So now to establish the order of accuracy of the RK2 method, we must compare its estimate for xi plus 1, which we had called equation 1, to that of the Taylor series formula, which we're calling here equation 2. And for this comparison to be useful, we have to convert some of the terms in the other expressions into some common forms. So we can do a two-dimensional Taylor series expansion of K2. So if you recall, K2 is shown here, and we can do this two-dimensional Taylor series expansion because you can see that here we've got our x is going to be at this point beta k1 away from xi, and t is at alpha h away from ti. So if we do this two-dimensional Taylor series expansion, really just writing down the first couple terms, so we're keeping the order h squared here term here. And we also note that k1 is equal to h fi ti. So we can substitute these terms back into 1, which is shown here, and we get the expression here. So we put our expression for k1 into here, and here, and this is all of this is k2. And we can expand this out and simplify, and we can call this expression 3. So comparing 2 and 3, we can match the coefficients of the corresponding terms. So you can see we have an xi in both equations, we also have, so in front of our fi, which we're simplifying that fi is f of xi and ti. So the coefficient of hfi is gamma 1 plus gamma 2 here, and in here it's just 1, so we can say that gamma 1 plus gamma 2 equals 1. The coefficient of this term, h squared partial f by partial t evaluated at I, and h squared partial f by partial t evaluated at I. Here we've got 1 over 2, and here we've got gamma alpha. So we can say that gamma alpha is equal to 1 over 2. And comparing our last terms, we can see that gamma beta is equal to 1 over 2. So these are three nonlinear equations in 4 unknowns. So we've got alpha, beta, gamma 1, and gamma 2. So we can use alpha as a free parameter and get the expressions shown here. So gamma 2 is equal to 1 over 2 alpha, beta is equal to alpha, and gamma 1 is equal to 1 minus 1 over 2 alpha. So with 3 out of our 4 constants chosen, we have a 1-parameter family of second-order RK formulas. And typically, the choice of alpha is equal to 2 is made quite frequently. So the RK formulas are often presented in a different but equivalent form. So for example, the popular form of the second-order RK method, or the RK2, with alpha is equal to 1/2, is presented in a predictor-corrector format. So where the first equation is the predictor, so xi plus 1/2, which we sometimes call xi star plus 1/2, is found using this equation, and then this is the predictor, and then this is the corrector to get us our actual estimate of xi plus 1. So the calculations proceed by recalculating the predicted value in the first equation, which is then used in the second equation, as you can see here, to obtain the corrected value at xi plus 1. It's the exact same method as what we just presented, just in a different format. So now we can use our linear analysis to gain some insight into the stability of the RK2 method. So let's apply the RK2 method to the model equation x prime equals lambda x. So we get our k1 is equal to h lambda xi, k2 is equal to h lambda times xi plus alpha h lambda xi, which we can expand out here. So we have this h lambda times 1 plus alpha h lambda xi. And then x1 is given as shown here. And if we choose alpha is equal to 1/2, then we get the expression shown here, which we can see that confirms that the method is second order accurate. Now for stability, we must have that our sigma is less than or equal to 1. So sigma here, from our previous result, was 1 plus lambda h plus lambda squared h squared over 2. So a convenient way to obtain the stability boundary, which is when the magnitude of sigma is equal to 1, is to set sigma is equal to I theta, which is equal to this polynomial 1 plus lambda h plus lambda squared h squared over 2, and then to find the complex roots lambda h of this polynomial for different values of theta. And we can recall that the magnitude of, or the modulus of e to the power I theta is equal to 1 for all values of theta. So we can solve this equation here for different values of theta, and that will give us different points that define the stability boundary. So if we do that, we get a diagram something like what is shown here. So again, this is the real lambda theta, and this is imaginary lambda theta. And we see that we get this stability region here. So on the real axis, the stability boundary is the same as the explicit Euler. So this goes out to 2 here, or the magnitude of lambda RH has to be less than or equal to 2 for it to be stable. But we see that there is a significant improvement for complex lambda. So compared to the explicit Euler method, we've got a lot more space in our stability boundary here. The method, though, is unstable for purely imaginary lambda, similar to the explicit Euler method. So it's just tangent to the imaginary axis here, and it is actually does not contain any of the imaginary axis. So let's look at this in a bit more detail. So we'll consider lambda is equal to I omega, which is a purely imaginary lambda, and substitute this into the expression for theta, or for sigma. So sigma was 1 plus lambda h plus lambda squared h squared over 2. So plugging in I omega for our lambda here, we can expand this out, and we see that this is the real part and this is the imaginary part. So the magnitude of the sigma is the square root of the real part squared plus the imaginary part squared. And if we plug those in and simplify, we get that sigma, the magnitude of sigma is the square root of 1 plus omega power 4 h power 4 over 4, which is always greater than 1, which means that the method is unconditionally unstable for purely imaginary lambda. So it is unstable for methods that produce an oscillatory solution, or for equations that produce an oscillatory solution. However, we can see that for small values of omega h, this method is less unstable than explicit Euler. So for example, if we consider the numerical solution of the method here, or of the equation here, where we've got lambda is equal to I omega, and if we want to solve this for 100 time steps using an omega h of 0.2, the numerical solution after 100 time steps can be written as y is equal to sigma to the power 100 times y0, where sigma is the amplification factor corresponding to the particular method. So for explicit Euler, our magnitude of sigma is the square root of 1 plus omega squared h squared. So with omega h is equal to 0.2, this is 1.0198. For RK2, this was our expression for sigma. So again, plugging in 0.2 for omega h, we get 1.0002. So after 100 time steps, the magnitude of y here is going to be this sigma that we get to the power 100. So RK2, we get 1.02. So it's unstable, but it is slow growth. We only have a 2% error after 100 time steps. Where for explicit Euler, if we do the same thing, we get 7.11. So it grows much, much faster. We can also look at the phase error for RK2, which is obtained from omega h minus the inverse tan of the imaginary part over the real part. If you recall, our phase error is calculated from omega h minus theta. So here theta is this inverse tan of imaginary over real, which plugging in our expressions for the imaginary and real parts of sigma, we get this. And now to expand this out and understand the phase error, we can look at the series expansions of these expressions. So 1 minus x to the power minus 1, or 1 over 1 minus x, can be expanded as 1 plus x squared. An inverse tan of x can be expanded as x minus x cubed over 3 plus x power 5 over 5 minus x power 7 over 7, etc. So if we combine these two expansions, we can expand out this term as shown here. And this can be simplified to give omega h plus omega cubed h cubed over 6, etc. So the phase error then is omega h minus this expression, which is equal to minus omega cubed h cubed over 6. So this is not much better than the explicit Euler method, which was omega cubed h cubed over 3. So it's a little bit better, but not much. But it gives us a phase lead instead of a phase lag because we've got this negative here. Now, the most widely used Runge-Kutta method is the RK4, the fourth order method, which was presented in a previous lecture. So just to recall, the estimate at time step xi plus 1 is equal to xi plus h over 6 times k1 plus 2k2 plus 2k3 plus k4, where K1, K2, K3, and K4 are evaluated as shown here. Now, to analyze the stability of the RK4 method, we apply it to the model problem x prime equals lambda x, which leads to the expression shown here. So you can see this is our sigma. You can see that this, we match e to the power lambda h all the way up to the lambda 4 h4 over 4 factorial term, which confirms the fourth order accuracy of the method. Now, the stability diagram is found by finding the roots of the fourth order polynomial with complex coefficients, which is, so we take our sigma and we want to find when this is equal to e I theta for different values of theta. And we can consider values, different values of theta between 0 and pi and solve this, this polynomial with complex coefficients using some root finding method. And what we get is the stability diagram shown here. So RK4 has a large stability region on the imaginary axis. You can see it goes all the way from here to here. There are actually two small stable regions corresponding to a positive real lambda. So these regions here, where the exact solution actually grows, so it's artificially stable for these regions. And you can see that we get quite a big stability region along the real axis as well. And this is just a comparison of the stability regions for both RK2 and RK4. And so RK4 does actually contain a large portion of the imaginary axis, so it should be stable for oscillatory solutions within the appropriate range of lambda h. So let's look at an example. So let's consider the ODE here. So y double prime plus omega squared y equals 0 within initial conditions y of 0 is equal to y naught and y prime of 0 is equal to 0. And we're going to solve it using the RK2 and RK4 methods. So this is a second order ODE, so the first thing we need to do is write it as a system of two first order ODEs. So we can define y1 prime is equal to y2 and y2 prime is equal to minus omega squared y with these initial conditions. So y1 of 0 is equal to y naught and y2 of 0 is equal to 0. So using RK2 with alpha is equal to a half, we can use the predictor corrector format. So this is our first equation, the predictor part. This is the second equation, the predictor part. And then we get the first equation, the corrector, and the second equation, the corrector. And we can also use the RK4 method to advance similarly to find the values for both y1 and y2 at each time step. And if we do this for y naught is equal to 1, omega is equal to 4, and h is equal to 0.15, we see that RK2 is mildly unstable as predicted by the linear stability analysis because this system has a purely imaginary lambda, and RK4 is stable as predicted and it is highly accurate. As you can see in the figure, the black line is the exact solution, the blue dashed line is RK2, and the orange line with the circles is RK4. So you can see that it is stable and produces a very accurate solution with virtually no phase error or amplitude error for this problem.